alcohol protection group. The idea behind protecting groups is if I had a reaction, let's say like this one, and I wanted to do hydrobromination to create this group, so if I just wanted to react HBr with this alcohol with this alkene to get addition across the double bond, the problem is that this alcohol is also reactive with HBr, right? So I could protonate the alcohol, and so I would have also ended up substituting the alcohol through an SN1 acid addition type process to get this product, right? And then again, depending on how many equivalents of HBr I put in there, I might have done this reaction first and ended up with this product. So I would have gotten multiple products from this reaction because the reagent I want to react with the double bond is also reactive with the alcohol. So this is the concept of protecting group. It's very similar to what happens in storage of sugars. So sugars are cyclic. The reason they're cyclic in storage formats is that makes them unreactive. And when we get to aldehydes next semester, you'll see that what happens with a sugar is that most sugars are either ketones or aldehydes, and we can actually protect them in a cyclic form as a hemiacetal or an acetal. Okay, so that protects that group so it doesn't react. So if I think about starches, what I'm doing with starches is taking a sugar molecule and I am lining them all up in a cyclic format and actually protecting them from reaction until I need them to react. And so this is a very biological type process. You see things being protected to being stored or to make sure they don't react with something else, and then a deprotection, right? Removing that protection and having them react. So when a sugar goes from a cyclic form to a straight chain form, then it's an aldehyde or a ketone, then the reaction starts. Okay, so I can break it down into this energy molecule in the case of sugar. Okay, so the idea here is that we're going to take some substrate, right, like this substrate here. I'm going to protect that. And for now, we'll just put new functional group. So I'm going to change that functional group of that alcohol . I'm going to do my reaction. And then I will deprotect. And the protection and deprotection process is important because I want to end up what I started with. So you can think about it, I'm protecting, I'm hiding it. I'm hiding the reactivity of that group. Good protecting groups are easy to put on and easy to take off, meaning they have a high yield reaction to put them on and they have a higher yield reaction to take them off. There are several, but the one we'll focus on is silyl ethers. It works in most cases. Okay, so we take trimethyl silyl chloride and triethylamine. We love abbreviations in organic chemistry. So this one here, trimethyl silyl chloride, is known as TMS. chloride. So it's this TMS group, kind of like our tosylates, right? We use the TS. Here you'll see the TMS. This goes through a hypervalent mechanism. To make the silyl ether. This is a good solid reaction, pretty mild conditions. Again, what you'll see often is it abbreviated as TMS. To remove this, we have two main ways to deprotect. So this was the protection group or protection step. To remove that deprotection, we can use tetrabutyl ammonium fluoride. So that is the salt. And I'll put aqueous work up here. Sometimes you'll see that, sometimes you won't. We need a proton source, so that's why we have an aqueous workup. And it is as simple as just putting water into the reaction when you're working it up to get the proton source. So if we looked at this reaction here, the one we started with, we would start with the alcohol and the alkene. Add the reagents to protect, turn that into the silyl ether. Then we can do the reaction. To give us the bromination, the hydrobromination. To get us back to the product. Okay. You're going to see this protection, deprotection process several times. Again, this is a very biologically important process. You'll see groups being added and mechanisms and enzyme mechanisms just to protect a group, and then reactions occur, and then they just remove it at the end. Synthesis of proteins can be done by protecting one side of the protein, and then the protein being synthesized. So this protection, deprotection concept is something that's very prevalent in biochemistry and biological synthesis. Okay. All right. Okay, so that cleared up our alcohol. So now you should have all of those alcohols. Again, this one won't be on the test, but could be on the final. So let's look at epoxides. And so two old reactions. All right, we can form an epoxide with a peroxy acid. Here is MCPBA. MCPBA is metachloro. Oops, that is parachloro. Peroxy acid, right? It's that double oxygen there that makes it the peroxy acid. That gives us an epoxide. So we saw that with the alkene reactions. So this is a reaction that you should prepare for the exam on Thursday. Another old reaction, old as in Thursday, last Thursday. We could take an alkene, react that with hydrohalogenation, halohydrin formation. Remember, this gives you the anti-addition, the bromine going up and the hydroxide group going down. And then what we saw was intramolecular ether formation. So if we deprotonate that oxygen, the oxygen is set up perfectly for backside attack. All right, so if we deprotonate that, we are set up for this to come in here, all right, to give us our epoxide. So we know two ways to form epoxides. Both of those are previous reactions. So halohydrin, right? We can do a halohydrin to stop there, but we can also take that halohydrin and follow it by a base reaction to form an epoxide. And of course, the peroxy acids, so MCPBA, the methyl version, any of the peroxy acids would do the epoxidation. Okay, questions about these? So we have seen ring opening before. We're going to get into some specifics, but remember that we did the dihydroxylation. Right, the anti-dihydroxylation, right? This is an old reaction. So we have seen that ring opening before. What we're going to get into here is specific. So there are some subtleties to ring opening, depending on whether we do it in this case, right, with the H3O plus, or if we had done, you know, sodium hydroxide followed by H3O plus, right? So in the top case, we're looking at an acid catalyzed. And at the bottom right, we're looking at nucleophilic promoted or base promoted ring opening. So we have two forms of ring opening to look at. In nucleophilic or base promoted ring opening, if we have a non-symmetric epoxide, we react that with a good base or nucleophile. So here we add sodium methoxide. The regioselectivity we're going to get is that the nucleophile is going to add to the least substituted side. And the stereochemistry, as we saw with the dihydroxylation, is we get backside attack. So therefore, it's going to be a trans, one on top, one on the bottom type process. Not really anti-addition, but it gives us an anti-style product. Okay, so let's look at the mechanism on this one. So we tack the least hindered side. So this is going to be, if you think about it, an SN2 style reaction. So therefore, we're looking for the least hindered side of the reaction of the substrate. So that's going to be the primary over the tertiary. So that's already formed my backside attack there. And then I just do a proton transfer with my solvent. To pick up a proton. So in base promoted or nucleophilic promoted, we look for the least hindered side. That's going to be the one that we're attacking. So if we think about it, this is an SN2 style process. We're looking for an SN2 style position to attack. An acid catalyzed ring opening so if we start with a similar substrate, so this asymmetric group here, and now let's take the same reagent, but let's put it in an acid solution. So H3O plus, here we have methanol and H plus, so sulfuric acid is our catalyst. In this case, what we end up with is attack at the opposite side. Of the epoxide. And our stereochemistry is still trans, right? We have one on top of one on the bottom. So we still get a backside attack. Since we have stereo specific control, that means we're not going through a carbocation. So that's the important part here when you look at the stereo control for the ring openings. Even though it's acid catalyzed, we're not going through a full carbocation. If we were going through full carbocation, we wouldn't have any stereo control. Now the regio selectivity, right, suggests that we have something that is SN1 like, right? So we've got a partial positive that we're going to be playing with, although we do not end up with a full carbocation. So just looking at these two things, you should be getting to the point where you can kind of dissect that to say that if there's stereo control, there's no carbocation. And if your brain didn't automatically jump to that, don't worry about it. You know, it takes a while. But there are clues to tell you what's going on. Okay, so what happens in the first step here is we do a protonation. And so I've already protonated the methanol to give us this protonated methanol species. And then at this point, what we think about is that we have two possibilities. And this is, remember our bromination for the halohydrin. This is a similar idea. So if we have, you know, if we start stretching that, a three-membered ring is not going to be that stable. It is stable enough to put in a bottle, but it's not like it's happy about it. Okay. If we have both of these, this is going to be the more stable of these two species. Because it can withstand more of that carbocation because this is a tertiary position. Let's go back to our, so we never end up breaking the ring with the acid, but since the more electrophilic position is the more substituted position, as shown here, right? This tertiary position, that means that we get attacked at the more substituted position. It's a stronger electrophile. That forms our stereo control. And then we just need to get a proton transfer. To get us our product. Questions about the ring opening? So in the base promoted or nucleophilic promoted, we should be thinking SN2-ish, right? So we should be thinking least hindered. So where can the nucleophile attack that ring to ring open at the least hindered position? That's the driving force in the nucleophilic promoted as far as the regiochemistry. In the acid catalyzed, it's like the halohydrin, which side of the positively charged three-membered ring could withstand more of that positive charge? The more substituted side can have more charge, meaning it's more electrophilic, and that explains the regioselectivity of the acid promoted. So I can switch. There's not always can I decide which way I want to go, but there are some substitution patterns where I can just change it from a base to an acid, such as this one, right? I can either use methoxide to do base promoted, or I can use H3O plus, methanol in acid and do the acid catalyzed. And I can get two different products by selecting those. Questions about these? Okay. Let's do some practice problems from for the quiz. So remember, we went back quite a ways. So alkenes, alkynes, radicals. alcohols and ethers. Okay. So alkenes, alkynes. The nice thing about those is that they're similar, so learn them and then learn the slight differences. Radical reactions, alcohols, and ethers. And we haven't focused much on nomenclature for these. Okay. We're really focusing on mechanisms, predicting products, and selecting reagents. Okay, so let's look at a few reactions. Let's predict some products. Okay, so let's take a couple minutes. Think about these and predict the products. Okay, in the first case, start with the alkene. The alkene is going to react with the bromine. Remember that the bromine makes a brominium ion, which is cyclic. So we have a slightly different mechanism here. And then the bromine comes in, the bromide comes in, does a backside attack. And my product is going to be the dibromide. And if you showed the enantiomer of that, that's fine. What you can't show is the diastereomer. Okay, on the next one, we have an ether. The ether is really only reactive with acid conditions, so acid cleavage. So again, let's look at the mechanism. So HBr, oxygen is going to react with the acid. So we get a proton transfer. Then we have the protonated form. Now, if one of those two sides can do an SN2 style attack, that's the one that's going to react first. So we do have a primary here. Okay, so we get the bromine. That's one of our two products. And since it's set at excess, we'll get this to occur one more time. So protonation. Let's see, let me give myself a little bit more room. Now, in this case, it's not likely going to do an SN1 type process. So what we'll end up is forming the carbocation. And then the bromide will come in and react with that carbocation. All right, so if it's tertiary, I'm not going to get a very quick SN2 reaction, so we'll do an SN1. So if I use excess, I'm going to end up brominating both sides of that ether. Questions about this one? You can do one equivalent. Okay, so it could do one equivalent, and then you need to know which side is going to end up with the alcohol and which side would end up with the alkyl halide. Last one, we get a reduction. Okay, to give us the alcohol. Okay, questions about this one? You should know the mechanism for the ester. I didn't specifically go over the mechanism for the acid. It's slightly different as there's a little tweak right in the middle that we didn't cover. So you'll be responsible for the ester lithium aluminum hydride reduction, but not the acid. Okay. Okay, questions about any of these? It's pretty straightforward. All right, let's do some select the reagents. Okay, let's go ahead and take a look. Okay, when you're looking at these, you need to start by thinking about what you're doing, right? We're starting with an alkene. You know, I would write that down, right? I'm taking an alkene to what type of dihydroxyl? Okay. I've got a syn addition of a dihydroxyl. You should think about these as you're doing your practice, even on the exam. You know, keep a piece of paper handy and just make some notes. So an alkene to a syn dihydroxyl, can we use the epoxide followed by ring opening with acid and water? No, that would have given us an anti, right, trans. So therefore what we want with this one is the osmium tetroxide, right? So we can use osmium tetroxide followed by sodium hydrosulfite, but you could have used KMNO4, right? So we needed some type of either osmium tetroxide or manganese tetroxide reagent. Similarly, I'd start by looking at our functional groups, and this is where the flashcards can help you, right? So alkyne, that triggers your mind to think about those functional groups. So what kind of alkyne reactions I have, and I'm going to a trans alkene, right? A trans alkene, can I use a catalytic, either catalyst or poison catalyst to get this? No, both of those are metal surface type catalysts that are going to give us syn. So what we want here is a dissolved metal catalyst, right? So the sodium in ammonia or lithium in ammonia. Sodium, lithium work fine. You don't usually see potassium. But it could also work. Potassium has a tendency, if the ammonia is wet, to catch on fire. So as you go down the table, it gets a little bit more reactive. So the next one is a little bit advanced, but is important to think about. What do I have to start with? I have a ketone, right? And I have an ester. I end up with an alcohol and an ester, right? So therefore I want something that'll change the ketone to the alcohol, but won't do anything to my ester, right? If we think about this, this is a reduction. So what reduction will reduce a ketone to an alcohol but not impact the ester? Well, it turns out that sodium borohydride will react with aldehydes and ketones, but does not react with esters. It does react with acids, but not in the way that you would want it to. You put an acid and a sodium borohydride and it just forms hydrogen gas. Now I could have, if I would have used lithium aluminum hydride, so if I had changed this to lithium aluminum hydride, I would have reduced both of those. Okay. And again, remember with the hydride, the sodium borohydride and lithium hydride, being selective about your equivalents is difficult. So it'd be hard to get just reduction of one of these without the reduction of both. And it'd be hard to pick which one you're going to reduce. So with sodium borohydride, because it's not reactive enough to react with esters, I can reduce a ketone or an aldehyde in the presence of an ester, but I can't do that in reverse. Okay. When we get to aldehydes and ketones and esters and acids, you'll see some additional reagents that will help with some of these processes, but that'll be next semester. Okay, questions about these? Okay, let's do a mechanism one. let's draw this mechanism to turn this alkene into the least substituted bromide. Okay. If you're stuck, remember this is a radical reaction. And radical mechanism has 3 steps: initiation, propagation, and termination. So we need to show those 3 steps. Okay, so let's take a look. So first step is going to be initiation. Spelling that wrong. So for the first step, we're going to use these half barbed arrows or fishhook arrows. Form the radical. And the second step of the initiation, that radical is going to react with HBr to give us a reactive species. So we're going to extract this proton to form the bromide radical. Okay, and then the bromide radical is going to be a reactive species. So that gets us to propagation. So in the propagation, and I'm going to invert my substrate here just to make it easier. Okay. I'm going to get my radical to react to give me the more stable radical, which means I've got the bromine attached here at the end, forming the secondary radical. So remember, radicals follow similar stability rules to electrophiles. And then that carbon radical does an abstraction of a proton from the HBr. Oops. Keep my color theme going. Plus then, and again, propagation mechanisms should end up with the same radical you started with, right? So think about propagation of, let's say, wheat, right? You plant your wheat seed, your wheat plant grows, then you take a portion of your wheat seed and you put it back in the ground for next year's season, and then you eat the rest, right? So propagation. So we take the bromide radical, goes in, and the bromide radical should come out, and then you should always show your termination. And termination is any 2 radicals, right? So we could have terminated right off the beginning. And I'll show the half barbed arrows in a second. Okay, and in this one, right, there's a bunch of ways to think about this one. So we could have just had the hydrogen peroxide pop back together. We could have the bromine radical react with the carbon radical. Any two radicals that terminate, right, stops the reaction. So is this heterolytic or homolytic reaction? This is a homolytic, right? Each side is getting the same thing. Instead of heterolytic would be what we saw with anions and cations, right? Okay, questions about this one? Let's try a few more reactions. Again, just practice for the exam, a little bit of a review. Okay, so let's take a couple of minutes. Predict the products of these reactions. Include regio and stereochemistry if it's there. Okay, and the first one, right, the nucleophile is going to attack the electrophile. Leaving group's going to leave. That ends up giving us addition of the hydrogen to form the more stable carbocation, which means our bromide, which is now the nucleophile, will attack the carbocation. So nucleophile attacks the carbocation. So we get bromine, hydrogen bromide addition with the bromine at the more substituted position, driven by the stability of the carbocation and the intermediate. In the second one, we form the ketone. So if we remember the process, we end up getting adding the alcohol to the more substituted side. But then we get tautomerization. right, to the ketone. So we form the enol then tautomerizes to the ketone. Selectivity of the functional group is similar to the alkene, right? We form the more substituted alcohol. That alcohol then tautomerizes to the ketone. And the last one, we get abstraction of the proton, forming the alkoxide. Then the alkoxide reacts with the electrophilic carbon. Okay, so nucleophile attacks electrophile. And that ends up giving me the ether. And this is known as whose ether synthesis? This is the Williamson ether synthesis, right? It's Williamson. Okay. Questions about these three reactions? Let's try a few more. Lots of reactions for this exam. Okay, so let's take a look. So in the first one, we do the diisoamyl borane. That ends up giving us this boron species. And then that with the hydrogen peroxide and base gives us the enol. Oops. Right, but the enol doesn't stay the enol. The enol tautomerizes to the aldehyde. So the diisoborane reacts similar to BH3 for the alkene, gives us the alcohol on the terminal position, the least substituted position. But since it's an enol, it tautomerizes to the aldehyde. Okay, the next one, we do an oxidation of a secondary alcohol, right, to a ketone. So secondary alcohol to a ketone, we could have used one of our reagents that give chromic acid, such as chromium trioxide and acid, or we could have used sodium dichromate and acid. We also, because this is a secondary going to a ketone, we could have also used PCC reagent and methylene chloride. So that's pyridinium chlorochromate. So any of those three chromium-based oxidants could give me this product. Okay, the last one, NBS, is N-bromosuccinimide. Right, this is a radical reaction that works with allylic and benzylic positions. How do I get this? Okay, the allylic and benzylic positions. So what we need to think about is what is our benzylic position? And that's this position right here. So what we'll do is do a radical reaction to get bromination in the benzylic position selectively. So these are high yield reactions that give either the allylic bromination or the benzylic bromination. In this case, there's only benzylic possible. Questions about this one? Let's do another mechanism. Let's do the tautomerization mechanism. And let's do the base promoted tautomerization. Okay, let's go ahead and take a look. So first, I'm going to do an extraction with the base. That's going to give us the oxygen negative. That's going to come down here, pull off the proton, water, to give us our ketone. Question about the tautomerization? Okay. Let's do a couple of multi-step to end up. Okay, so starting with this acetylide, and I'm going to put 3 arrows. 3 arrows just signifies as many steps as you need. Okay, this is, we could do a retrosynthesis. We'll talk about that more after the exam. But here, the 3 arrows is just my way of saying as many steps as you need. Let's take a couple of minutes. Remember your carbon structures. Count your carbons. Think about your functional groups. Okay, let's go ahead and take a look. Starting to run out of time. Okay, the first one of the things that we should notice is here we have 2 carbons, right? And here we have 1, 2, 3, 4 carbons. So we're going to have to be adding at least 2 carbons. We're also ending up with an aldehyde, right? It's sometimes helpful to know how many ways you know how to do that. Well, I really only know 2 ways to make an aldehyde, right? I could take a primary alcohol, right, with PCC to get an aldehyde, right? Or I could take the alkyne with the diisoamyl borane, and you're not going to be able to read this, right? Sodium hydroxide to get the aldehyde. So I've got two ways to make an aldehyde, and I need to add carbons. I only know a couple of ways to add carbons at the moment. One of them is starting with the acetylide. So if we start with the acetylide, what do we want to do first? I mean, the acetylene, we want to make the acetylide. So we add sodium ammonia, amide, sodium amide. That gives me this, right? Then I want to add an electrophilic carbon, so something like the bromide. I add two carbons because I want to extend it by 2. So that gives me this. And I inverted it. So notice I kind of flipped it around. And then last step, I can use the diisoamyl borane, right, followed by the hydrogen peroxide in base, right, to get the aldehyde. So when you're looking at multi-step synthesis, first, always consider your carbon structure. There's only a few ways you know how to change carbon structures now. And then start thinking about how can I form, and you can think about what reactions can I do with the starting material, or you can think about what are the ways to make my final functional group, right? So that's why it's important to think about both preparation of and reaction of. So when you do your flashcards, make sure you have a set of both. Okay, questions about this one? Okay, so this acetylide reaction is a very useful reaction to extending carbon structure. The next one, if we look at our carbons, we have 1, 2, 3, 4, 5, 6, 7. Over here we have 1, 2, 3, 4, 5, 6, 7. So we haven't added or removed carbons, but you can notice that my 2, right, is no longer attached to my 7, right? So I've cleaved that bond. So there's going to be a carbon chain. It's not an addition or a deletion, but I am cleaving a carbon-carbon bond. You'll also notice that I have functional groups, and the functional groups are on 2 and 7, which is the same place I had the alkene, right? So that's also something. I'm not having to move any functional groups. So if we think about this one, what we need to do is break open this ring. How many reactions you know that can break open a ring? At this point, only one, right? So the first step is going to be ozonolysis, right? So ozone followed by hydrogen sulfide, like sodium hydrogen sulfide, or other reducing nickel, zinc, other reducing agents. That gives us the ketone, and the aldehyde. Okay, so that gives us our main carbon change. It ends up giving us, again, if we look at our numbers, so 1, 2, 3, 4, 5, 6, 7. So we have our ketone and our aldehyde in the 2 and the 7 position. How do we go from an aldehyde and a ketone to alcohols? Well, we can do a reduction with sodium borohydride and an alcohol. So sodium borohydride, clean that up. Okay, questions about this one? Okay, all right, that's time. So the test